did it. It's a lot to set up. Good morning, class. Hope you had a great weekend. Today we'll finish up energy. We're essentially there. I just have a few loose ends. I'll review a few, I'll check our understanding about momentum and energy with some clicker questions. And then we'll move on to energy. No, not energy. Projectile motion on chapter 10. And I'll tell you more about that when we get there. Do you have any questions about momentum and energy? That's fine again. I just never liked my instructors that never gave us a chance to ask any questions. So giving you the chance. All right, then. We know by now that work is force times distance. You apply a force over a certain distance, you do work on something, and work changes its energy or transforms it from kinetic to potential or vice versa. At the end of last time, it was quick, so power, P, is energy per time. And this works no matter what form of energy you're talking about. This will work with electrical energy, as well as kinetic energy and potential energies here. It's the rate at which you use up energy because of that time factor. So in this case, we can look at it as work over time. If you do a certain amount of work, you do a certain amount of work, period. But how fast you do it affects the power. And again, that units are the units of energy, which are joules, energies of time, which is seconds, a joule per second, which got defined as a watt after James Watt. So a watt and a joule per second are the same thing. There's one other term I'd like you to know about, and that's efficiency. This one should make sense. It's not going to be a big stretch of your mind here. Efficiency is just what you think it is. How efficient is some machine or something at doing something? It's just a percentage or a ratio. So it's the, let's put this as useful energy output. Now what you get out of the system. You know, if something does work, a machine does work, this is the useful energy output that you get from it. You know, a horse, you hook them up to a plow, and the horse can exert so much energy, do so much work. That's what you're going to get out of the horse. And you divide it by the total energy inputted. So it's just a ratio, fraction of what you get out versus what you put in. Tells you how efficient something is. So I wrote that all out because it's a little more technical, but I generally just think of it as energy out, energy in. Does that make sense? So example, where does the energy come from for the horse? Does the horse require energy to work? Yeah, in what form? Fuel, food, yeah. You're going to feed the horse, I hope. So, you know, if you could add up the cost, the price of all the food you need to feed the horse versus maybe the money you get out from his energy. You know, it's that idea. Technically, it's energy, not money, but you get the idea. For you know, your laptop, it runs, it does work, calculations, electrical processes, but you have to plug it in. It requires energy to run. So this is the energy in. We could measure how much electrical energy has to go into it. Calculate all of its processes. And what do you think its percentage is? What percentage out do you think we get versus what we put in? 1 to 1? That would mean it's 100% efficient. This fraction would be 1. And I'm here to tell you there's no machine that's 100% efficient. That's one reason I wrote this word. And you guys already know this. Where do you think some of this energy ends up, other than doing calculations and processes? Heat, yeah. I mean, it's a laptop. You set it on your legs and you get warm. You can feel the heat coming out. Yeah, that's energy. So total energy is always conserved. The total energy in always equals the total energy out. So in that sense, it's always 100%. But this machine, some of that energy out is from heat, which isn't useful to us. It's not helping us do anything we want to do. Same with a horse, for that matter. Eats the fuel, the food, the hay, and the horse is going to heat up, perspire. That's some heat energy lost from our system, which is why this numerator is a little less than the denominator. Actually, most machines aren't even close to 100% efficient. This gets into the laws of thermodynamics, which I've chosen not to cover this semester so I could show you some other things. But it basically says you can never have a 100% efficient machine because there's always some energy that becomes not useful. If you've heard the terms entropy, that's where it comes in. Like your car, they vary from engine to engine, but they're not even 50% efficient. Most things are fairly wasteful. So it's surprised we get anything done, right? But that's what it is. That's all you have to do. Energy in versus energy out. So if we bounce a ball, this is roughly a meter. Let's say this is ground zero, height 0. You raise it up about a meter. What's its potential energy? mgh. Let's see, did I write there? I didn't on this one. So we'll just leave it as mgh. So yeah, it has a gravitational potential energy of whatever its mass is by the acceleration due to gravity, 1 meter up. So we'll call it 1 unit of mgh. That's what it starts with. Let's see what it ends with after it rebounds. Right about here. Yeah, 50 or 60%. That's the efficiency of this. Because you only got a half to 0.6%, not 0.6%, but 60% of it back. How much did you lose? 40%. That did not return as useful output. Where did it go? There was friction between here, which heated this up and this. There's air resistance, which also turned into heat. And something we haven't discussed as much is that this squishes. And it takes some energy. It takes work, a force on this to deform it. So there's some work done on the object itself to flex it. Of course, it rebounds back. But sometimes that flexing gets turned into maybe internal energy in the molecules. And some of that doesn't always come back either. All of that left our system. It's still in the total energy, but it's no longer in the form of gravitational potential. And so we don't get it all back in that form. So for efficiency, yeah, you would just put this mgh. Let's say this is the initial height. the initial gravitational potential, then the final would be that new height it rebounds up to. This is energy, this is energy. So the efficiency is just the energy out, the final, what we ended up with, versus what we put in. So mgh of the final height, mgh of the initial height. You can see in that case, it's just the ratio of the difference in the heights that you guys just told me. It's nothing too complicated about efficiency. But there's a few examples for you. Questions? Okay. Simple machines don't magnify or amplify energy either. They don't magically create some perfect machine. Again, because the energy in and the energy out ideally are the same, but there's probably some friction in a lever and the pulleys, so you actually lose a little in that also. So they're not even 100% efficient. But ideally, it's the same amount of energy. You got to do this. Whatever work you do on one end is the same work you get out on the other end. A little less, you know now. But you can use simple machines to amplify force. I can do a little force over a big distance to make something I can't move, get more force over there, but just move it a little distance. You can also use them to, maybe you want to move it a bigger distance to amplify the motion. That's how our muscles work. You ever thought about that? Here's a lever, your bicep. You got your muscle, your bicep, that attaches right about here. Here's your pivot point, your elbow. So you're pulling up right here. Force, distance. See how far that moves? Not very far, does it? But over here, you get a big range of motion. See how far it moves? So at which point do you think the force is larger? Same force? Any other takers? Let me ask it this way first then. At which point do you think there's more work done? Here or here? We just said they can't magically amplify energy. So it's the exact same work done here at this point, the force trying to move this point, as whatever is in your hand, you know, your force there moving at that distance. A lever just changes the location there in that sense. Does that make sense? It's the same work done here as it is here? Absolutely, my hand is moving a greater distance. This is one of these games. If energy is conserved, ideally, the work in each spot is the same. So we have this game again. Let's look. Well, we'll take this lever. Here's our pivot point, our elbow. I know, it's high tech here. And here's your bicep, your muscle. Over at this point, a force trying to move this a certain distance, and maybe you have a big weight in your hand over here, and you're trying to lift that force. Actually, the weight is trying to pull your hand down. So you have force 2 versus force 1. That's the idea. So I'm saying that the work here is the same as the work there. Since this one moves less distance, that's this side. F1 is huge compared to F2 over here. Does that make it more visible? Just like our lever with the lead brick. So again, you can't use simple machines to magically create energy, get more out than you put in. The work has to be the same everywhere in a simple machine, ideally. There's friction. But the force and the distance, the product, those can change. I can change the force. And this is one where my ultimate point here is a lot of people think, yeah, we're built to have mechanical advantage and get a lot more force out. This is one case where it's the opposite. We're built to actually increase our range of motion. Your bicep has to exert a lot more force to lift a weight. This isn't much weight, but it gets the point across. It's a lot more force in your muscle than needed to just lift this straight up and down. But that's so we can actually move a big distance instead of being limited. I saw some B-rated sci-fi film years ago, and they had these aliens. They looked funny. They had these big skin flaps, like from here to here and here to here. Why? Because it was covering up their biceps. Their biceps weren't attached here. They went from here to here. It's like getting more mechanical advantage, right? They were a lot stronger than humans, but they could only move things a little bit. So there's advantages and disadvantages depending on which side you're on. You can increase the range of motion with the distance, but you got less force. Or you can move something less far, but have a lot more force. Either way, the energy is the same. Have I harped on that enough now? Is it clear? Well, I think that wraps up our energy. Let's check your understanding. I prepared some questions for you. Going to start with 2 momentum questions, and then I'll ask you a couple energy questions. And we'll see how we're feeling. So there's the info, so as you log in. Oh, open the question, Adam, that would help. All right, polling's now open. So this is a collision between a big fish and a small fish. You got a small fish just sitting there minding its own business, not moving. And here comes big fish. Wow, wow, wow. Chomps it and keeps going. Precursor question. Is this an elastic or an inelastic collision? Do they bounce off each other and rebound, or do they stick together? Yeah, if it's eaten, it's inelastic. They stick together. This is conservation of momentum. Think about the total momentum before and the total momentum after. Ten. 9. Oh, it's not logging in for you yet? You guys on Uconnect? Yeah, it comes and goes all right, that's for sure. I can wait a little longer. I'll give more clues. You keep struggling a bit. What's the big fish's momentum before the collision? Mass times velocity. The big fish's mass times his velocity. What's the little fish's momentum before the collision? 0. Very good. So the total, it's all the big fish, right? Afterwards, who's moving? Only? Yeah, think of the little fish in his belly now, if you will, or his mouth. Yeah. They're both moving with the same velocity. Yours worked? 10? Yeah, they're moving together. The big fish just ate the small fish, so they move off together. Repeat that?
You said they have the same velocity, not that he's still moving with the same velocity.
Correct. Correct. They have the same velocity afterwards because they're moving together. It's not necessarily the same velocity the big fish started with. That's the point of the question. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Oh, overwhelming B. Yes. For those of you that got it. For the few that didn't, what's the new mass now of the system after the collision? It's bigger. Before the collision, it was mv, big fish mass times its velocity. After the collision, it's big fish's mass and little fish's mass moving together. Since the total mass went up, the combined velocity has to go down to keep momentum, the total momentum, conserved. Does that help? It's like the big air cart running into the small air cart, and they stuck together. They increased their mass by combining, so they moved off a little slower than the big one came in at. Exact same thing. Okay. With that, let's see this follow-up question. Go. Same question, but instead of asking about the speed, what's the momentum? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Most of you, eh? That is correct. The big fish had all the momentum before. So that total momentum before has to be the total momentum after. The big fish, now I'll admit, this question is slightly confusing in realizing the little fish is now part of the big fish. They're together. The little fish is no more. So the total momentum after, though, is still the same. Okay, let's ask some energy questions. Forced to lift a crate, what's the work done on it? I'll give you a clue, too. 200 kilograms represents the what? Not the force. Weight is a force. The mass. Kilograms is the unit for mass. That's the mass. Work is calculated how? Force times distance. And they gave you the mass. Oh, yeah. Glad I gave you that clue, I guess. Okay. Issues with this either rotating or falling off. Let's try. I'll just put it here and hopefully I don't snag it. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. The majority's D. The majority does have it. Let's clarify. So if the mass is 200 kilograms, what's the minimum force required to lift this crate? How'd you get 2,000? Mass times the acceleration due to gravity. You have to at least overcome its weight to lift it, right? So it's its mass, 200 kilograms, times the acceleration due to gravity, 10 meters per second squared. 200 times 10 is 2,000. So this thing weighs 2,000 newtons. That's the force you need to lift it, 2,000 newtons. How far do you lift it? 2 meters. 2,000 newtons times 2 meters is 4,000 joules, force times distance. The time was in there just to throw you off. So again, I know force times distance. You just had to find the force first. Remember what that was from Newton's second law. Questions? All right, remember this. The energy, the work done, is 4,000 joules. Go. It's the same question, except it's not asking you for the work. It's asking you for the power. Your clue, how do you find power? What is power? Energy over time. It's the rate at which you are doing this work. Work over time. Same as energy per time. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Overwhelmingly answer B. You're right. 4,000 joules energy in 4 seconds. 4,000 divided by 4 is 1,000 watts. Joules per second. Same thing as a watt. If a charging elephant has kinetic energy, what must it also have? Potential energy, momentum, work, or all of them? Basically, if you know an object, in this case an elephant, has kinetic energy, that tells you something. What? Ten, 9, 8, 7. Tell me when you get it working. 5, 4, 3, 2, 1, 0. Most of you think momentum, but a quarter of you think it also means it has potential energy and work. From the O's, I can tell who thought it had it all. So if it has kinetic energy, that's the energy associated with movement. So it's moving, it has a velocity. If it has a velocity, it has to have momentum. So we know it's at least B. Give me an example of something that can have kinetic energy but no potential energy. If it's moving horizontally on the ground, relative to the ground, we would say it has no potential energy relative to the ground. Or our pendulum, our bowling ball pendulum, at one point it was all kinetic, but it had no potential at the bottom. But at the top it had all potential, no kinetic. So that already says the answer is just B. Why does it not work? Work is force times distance. You can apply a force to something and make it move and get to somewhere else. You did work on it. Here.
It's not having an effect.
I just displaced it from here to here. So I did work on it, but it doesn't have any kinetic energy. It does while it's moving, yes, but it doesn't necessarily have to. Just because something has kinetic energy doesn't mean it has work. Plus, I tried to emphasize, and here's a good review, don't think of objects as having work. They can't have work, just like they can't have force. Forces are interactions. It requires two things. They act upon each other. One doesn't have it. And work is just a way to transfer energy, to change kinetic energy and or potential energy. It's a transition. But the object itself doesn't possess it. It can do work on something, and you can do work on it. But it doesn't have work. Questions still about this one? I prepare one more. So you got this airplane that moves twice as fast as an identical airplane. So they have the same mass, but one's going twice as fast. Compare the kinetic energies. So same mass, different speeds. And we'll end with this one. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 2/3 C, but some of you think twice as much. What's the equation to guide our thinking for kinetic energy? 1/2 times the mass times the velocity squared. So if you go twice as fast, you don't have just twice the kinetic energy, you have 2 squared, 4 times the energy. Remember, so that means it will take 4 times as much energy to stop you also when you apply the brakes. Or run into a wall, whatever. So it's that 1/2 mv squared. Okay. All right, this is one of my favorite demonstrations. We call it the monkey shoot. I'm going to fire a bullet, this big wood slug here. This is a refurbished propane tank. We're going to put air in it and compress it in there. I'll release the air. A force acting over this distance will apply an impulse and change the bullet's momentum from nothing up to something, mv. It'll now have kinetic energy, 1/2 mv squared. When it comes out, it will release through an electromagnetic switch said monkey. Maybe I messed the setting up here. So the idea here, it's a classic problem where there's a hunter out with his gun. We'll make it a tranquilizer dart, you know, so we don't offend anybody. And he sees a monkey up in the tree. So he aims right at the monkey. Oh, look, he's scared. Right at the monkey. It's aimed right at it. But as soon as the hunter fires, thus the bullet leaves the gun, the monkey's smart. And he's going to let go. Because this switch will release him and he'll let go. Why would the monkey want to do that? To dodge the bullet. We're going to see if that works. And if it does, explain why. Who thinks it will miss the monkey? Because he's going to start falling, but the bullet's shot horizontal. You think it'll hit? Why? Gravity's pulling down on the bullet? Oh, but it's also acting on the monkey. Okay. Anybody think the bullet will go below the monkey? Why, Court? Yeah, as soon as it comes out, it will release the monkey. Back to okay. Well, that's all right. Let's try it. Let me get some air in there. Okay. You guys ready? 1, 2, 3. Boom! It worked. Oh yeah, you set this up. I've definitely shoot it more than once. Some instructors don't, but I'm like, no, we're doing this again. So you're right. And the point here is, as we move into chapter 10 with projectile motion, there's nothing new. You've learned all the kinematics, the motion equations, velocity, acceleration, in the first units. It's all the same here, except you have it happening in two directions. Two-dimensional motion is nothing more than two one-dimensional problems. You just have to do it twice now. You see how it's working in the horizontal direction, and you see how it's working in the vertical direction. People get into problems when they just try to mix them. So you're exactly right. The bullet, if I drop these right now, who hits the ground first? Very good. Why? Gravity is the same. Now let's be more specific. What about gravity is the same? The acceleration due to gravity is the same. So they accelerate at the same rate. Thus they take the same time to get there. Which one do you think the force is greater on? The bullet. A lot of you still missed that on the exam 1. I hope you looked at the answer key. The forces on these are clearly different because they have different masses, different inertia, but they're accelerated at the same rate, so they fall at the same rate. That's why even though the monkey was falling straight, the bullet falls vertically at the same rate. It just happens to be moving horizontally at the same time to get from there to there. And you saw they hit, where was it, about here-ish? Yeah. So it was kind of like this, slow-mo. Do, 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 do. See, vertically they fall in the same amount. Let's do it again. This time, we'll try something that some claim is a little smarter. Others don't. We'll try Cosmo here. But we are going to change it up, because it should be the same as the monkey if we just do this. So let's... Now what will happen? The bullet has to go up now. It's still aimed right at Cosmo to start with, but the bullet has to go up. Where Cosmo is still going to just drop straight. Who thinks we'll miss Cosmo now? Who thinks we'll still hit him? What's the acceleration on the bullet on its way up? Bless you. It's still negative 10 meters per second per second. It's just like tossing a ball up, right? The acceleration due to gravity is the same. Now, and now. It's trying to accelerate it down the whole time. It just happens to be moving up, so it slows down. And as it's coming down, it makes it go faster in the down direction. So the same thing is going to happen to the bullet. And the acceleration on Cosmo? Same. Let's try it. Let's try that. All right, ready? 1, 2, bye Cosmo, 3. Boom. Yeah. Well, I like it. Actually, I think I'll just leave it here. All right, everybody that video recorded, you got to send me a copy, please. That'd be cool. So yeah, we're still starting it here. So it's like, yeah, do. You get the idea. I made this little thing. This ropes and nuts hanging from a rope here. What I did was, where are we at? We're good. This is, say I drop something from right here. How far does it go in 1 unit of time? 1 second. You should be able to figure that out now. 10 meters. So this represents 10 meters. That's on a smaller scale. Obviously, it doesn't take a whole second. All right. How far does it fall vertically during the second second? How far does it fall after 2 seconds? We could do that 1/2 AT squared. So 1/2 of 10 is 5. That one I won't do in my head, because not everybody follows. 10 meters per second every second. After the second second, so 1/2 of 10 is 5. 2 squared is 4. 20. And the third second? 3. Oh. I realize why that doesn't sound right. Sorry. Yeah, okay. So that's the distance. The 3 squared is 9. It's because, we shouted out that it doesn't add up. That 3 squared is 9 times 10 is 90. Divided in half is 45. 4 seconds. 4 squared is 16. 16 times 10 is 160. Divided in half is 80. So the distance goes further and further each second because it's accelerating. I calculated these out. These are the same ratio for the same unit of time. Obviously, it's not a second. It's less than a second. But you can see it falls a little bit, and then a little further, and then a little further. So these represent vertically how an object falls. Now, the bullet had constant velocity horizontally. Was there a horizontal force acting on the bullet after it left the gun? Yeah. What was keeping the bullet moving horizontally in the air? It has momentum, but is there any force acting on it horizontally? technically air resistance. But we saw in dropping them straight, it's kind of minimal there. So basically, it had no reason to change its speed horizontally. That's like our hover puck that just keeps going, or you chuck something in space. That was like our constant velocity vehicle. It covered the same distance every unit of time, horizontally. Are you with me? So here's our two one-dimensional motions. Horizontally, same distance every second. So you can see these are spaced equally horizontally. It does move this way. But vertically, it's accelerating because of gravity. And so that one, it gets bigger and bigger each time. So let's see if I can do this. If I just take this ball and try to toss it. Does it follow that arc? Oh. That's why when we throw things, they make parabolas. Instead of just straight up and down. That way. It's a nice curve. Because horizontally, it doesn't change speed. Why would it? Its inertia keeps it going horizontally. There's no force horizontal, neglecting air resistance. But vertically, there is a force, gravity, and it accelerates. Let's do another one. And end. This one, I have two. Where'd they go? I scooched them. Okay, there's a spring loader. If I put it in here, I'm going to put one block in front so it'll get pushed horizontally. This one has a hole in it, so I'm going to slide it on the post. When I release it, the post is going to go that way. So it'll push this one. At the same time, what will it do to this one? It's just going to drop. It's like pulling the tablecloth out from underneath the plate. This one, its inertia will keep it in place, and it'll just drop vertically. So this one has horizontal velocity. This one has no horizontal velocity from the same height. Who will hit the ground first? You ready? Now this one's hard to see, so I suggest you listen. We'll see if we can hear when they hit. You ready? Yeah. Let's do it again. I'll shoot it even faster. I'll give this one greater horizontal velocity. And let's see if that changes. You ready? They still hit at the same time. Again, just because one has horizontal velocity doesn't mean that the Earth magically acts on it differently. It still accelerates them down at the same rate. That's the whole gist behind Chapter 10. I do want to remind you before you leave, and I ask your question, in Chapter 10, we won't be covering the part on orbits. I won't hold you to it. So as you're rereading it, you can not focus on that as much. Yes?
So if you were to shot a gun and there's kind of like that, you shot a gun and you dropped the bullet at the same time they hit, if the gun was level.
Yes, this is just, if you had a gun and you shot horizontally, at the same time you let go of something else, you just dropped it, it's no different than this. Because vertically, they fall exactly the same. Yes? Chapter which? We are skipping 8 and 9. We won't be coming back to them. All right, thanks everybody.